Hi, in this video we'll be looking at series. So we'll actually be considering, first of all, we have to introduce the idea of a series. Then we'll be looking at 4 tests to determine whether a series converges or diverges. The first test I call the divergence test. It's not always called that. You wouldn't see it called that in the reading material, but it's a fairly good name to remember it by. The second test is the comparison test. Then we have the limit comparison, also called quotient test, and finally the ratio test. So it's a lot to get through, so this video would be fairly long. Okay, so we've already seen what a sequence is, so consider a sequence AN. What we are going to do is we're going to take the first n terms of the sequence and add them together. Right, so we have A1 plus A2 up to AN, and we will call that S subscript n, right? Which we'll denote, we'll define as the nth partial sum. So when we talk about the nth partial sum, we just mean the sum of the first n terms. So for example, if I wanted the fifth partial sum, I would take the sum of the first 5 terms from A1, A2, A3, A4, A5. Right, now if I take the nth partial sum, right, that in itself is actually, you could think of it as a sequence, because I could have S1, S2, S3, S4, etc. And as n gets bigger and bigger, Sn, I could look at the limit of this. Alright, so if we take the nth partial sum Sn and we look at the limit as n goes to infinity, so we take the limit n goes to infinity of S subscript n, that's really just going to be the limit as n goes to infinity of the summation I goes from 1 to n of ai. Right? Because remember, Sn is just the sum of the first n terms. So basically I'm summing the first n terms and I'm taking the limit as n goes to infinity. What this really means is just the sum of all the terms of the sequence, right? Because if we're summing the first n terms and n gets bigger and bigger, eventually we'll cover all the terms as we get to infinity. And this is called an infinite series. So the infinite series, here, the limit as n goes to infinity Sn is called the summation I goes from 1 to infinity, is the summation I goes from 1 to infinity of ai. So whenever we ask for this sum, basically what we mean is we want the limit of Sn as n goes to infinity. Alright, this here is what the summation is defined as. Okay, now that that's out of the way, we say that if the limit of Sn as n goes to infinity, if this exists, if it exists and is some value s, then the series is convergent, meaning this summation is convergent, this sum is convergent, and it converges to that sum s. Right? Otherwise, it's said to be divergent. So similar to sequences. Alright, so what we are gonna be doing is trying to determine whether any given series is convergent or divergent. Now, one thing I want to mention here is, in general, when we are looking to see if a series is convergent, if it is convergent, we will not always be able to figure out what it converges to. Right? A lot of the tests that we're going to use, for example, ratio test, limit comparison test, those cannot tell me what the limit of the sequence is or the limit of the series is. Right? It does not tell me what the series actually works out to be. All it tells me, all the tests tell me, is whether it converges or diverges. Okay, now I mentioned at the start that the first test that I would normally look at is the divergence test. So it isn't always called this, like I said, but the divergence test basically says if the limit of an as n goes to infinity is non-zero, then the series, the sum of an as n goes from 1 to infinity, is divergent. Alright, now this is pretty intuitive. It can be used to solve some straightforward problems. All right, the reason why I say it's intuitive is because think about what this is. This here, remember a and the a subscript n, those terms form a sequence, right? So this summation, we're just taking the terms of the sequence and adding them together. Now, if you're going to add an infinite number of things together, if you want this thing to converge, then the limit of this sequence should be 0. Because if the limit is not 0, then you're going to keep adding things and changing the value, which means that you're never going to converge to a value. The only way this sum could work out to be a fixed value or a finite value is if the terms of the sequence actually get closer and closer to 0 until they eventually get to 0. Right? Having said that, you if the limit of an goes to 0, that doesn't actually tell me whether the series converges or not. Right? That's important to understand that, because we will see some examples where the limit of an goes to 0, but the actual sum is divergent. So just be careful with that. But what the divergence test says, what that says, if you take the terms of the sequence and you take the limit of that, if the limit is non-zero, then the series automatically is divergent, because you're going to keep adding non-zero things together, and therefore it could never converge to a value. Alright, so let's see a simple case where we could use that. So if I ask you to determine if this series converges or not, so we have the summation n goes from 1 to infinity 2n over n plus 1. So to do that, what you do is you can let this be an, and you need to find the limit of an as n goes to infinity. Again, remember how we do this for a sequence is we introduce the function f of x over the set of positive real numbers as the same function replacing n with x, and we find the limit of that as x goes to infinity. In this case, the limit works out to be 2, which means that the limit of an is also 2. But this here, because the limit is 2, it means it's not equal to 0. Right? What that means is that as we go further and further along in the sequence, we keep adding terms that are the value is very close to 2. And if you keep adding the 2 to itself, to whatever number you have, you're going to keep increasing the value. Right? So every time you add a term in the sequence, you increase by close to 2. And that means that this series will never converge, so it will diverge. Alright, so as I mentioned, you have to be careful because the limit being non-zero automatically means the series is divergent, but the limit being 0 doesn't tell you anything. Alright, so the converse of this, or if you take the opposite of this, it is not going to tell you anything. And a simple counterexample is consider the harmonic series. If I let an be 1 over n, we've already seen when we looked at sequences that sequence converges to 0. So as n goes to infinity, 1 over n goes to 0. But the series itself diverges. Right? And later on we will see something that actually, well, we're not going to see this actually we're not going to see a direct way of doing this, but we will see a theorem that tells us that. Alright, so there are some properties you should know for series. So suppose we have two series, sum of a and sum of bn, and the first series converges to a, the second series converges to b, then these things are all true. So if I take the summation of k times an, so a constant times an, I could factor the constant out of the summation and I'll get k times a as the answer. So what that tells me is that this series converges to ka. Also, if I create a new series where the terms are the sum of an and bn, so the sum of an plus bn is just going to be a plus b, and the sum of an minus bn is just a minus b. Right. One thing to note, right? Suppose I had a convergent series and I had a divergent series, and I add those terms. Because this one is divergent, when you add them together, it will diverge. So just be aware of that. If you add two divergent series, that's going into a different type of question. So I'll just leave this here for now. All right, now two important series that will help us when we get to the tests later on. First of all is the geometric series, which everyone should know. We have start in term A and then we multiply it by some common ratio R every time as we go. Now the geometric series, which is just the sum of all these the terms of the sequence, right, is given here. Now if the common ratio, the absolute value of the common ratio is less than 1, then that series converges to A over 1 minus R. If the absolute value of R is greater than or equal to 1, then the series diverges. Right, so that can be fairly important depending on the kind of questions that we have to deal with later on. So just bear that in mind. These are just some examples. I'm not going to spend too much time on these. Now the next one, which you might not have seen before, is very, very important for this course. Given a real number p, the p series is defined as the sum of 1 over n to the power p. Right? Please remember this and ingrain it into your memory. This is very important. You don't need to know the expanded form, you just need to know what the series is. It's just a sum, n goes from 1 to infinity, 1 over n to the power p. Now this theorem here tells us how we can use this. So if I have a p series, right, p series meaning I have n to the power p in the denominator here. If p is greater than 1, then this series converges. Now it doesn't tell me what it converges to, and in fact there's no way to know. Right? So all we know is it converges. When p is less than or equal to 1, it diverges. Right? So if p is, let's say it's 1 or it's a half or negative 1, then this diverges. Right? Notice when p is equal to 1, we get the sum of 1 over n, which is the harmonic series that I mentioned before. So this theorem tells me that the harmonic series diverges, but it doesn't tell me why, right? It's just a theorem that we have to use. We are not going to be considering ourselves with trying to prove this theorem. We're just using it. All right, so these are some examples of convergent p-series. So we can take p as 2, 1.5, 3, 4, etc. Whereas if we take p as 1, a half, negative 2, or 0, these are all divergent. Okay, so now we actually get into the tests for series convergence. So we already briefly mentioned the divergence test, which is the most straightforward one. The next three are the ones that require a lot more actual work to figure out if it converges or diverges. Now, the comparison test basically involves comparing two series. So the series that we are given is one of the series. What we need to do is find a second series to compare it with that we know converges or diverges and that we can use. How it works is basically this. Suppose I have two series, I have AN and BN. And let's say A1 is less than or equal to B1, A2 is less than or equal to B2, and that continues. So for the A terms are always less than or equal to the corresponding B terms. Now, if that is true for all of them, then when I take the sum, because I'm adding these terms, the inequality sign isn't going to change. So the sum of AN is going to be less than or equal to the sum of BN, which means that this series, if it converges to a value, and let's say both of them converge to a value, then this series will be less than or equal to the value here. Now, what happens if the sum of Bn diverges? Now, remember what happens if the sum of Bn converges, is what I meant to say. If the sum of Bn converges, remember, sum of An is always less than or equal to this. So if this thing converges to a finite value, then this must also converge to a finite value. Right? Right? Yeah, so if this converges to a finite value, this always converges to a finite value, assuming that they are positive, right? We're just going to assume that they are positive for now. Right? Because this theorem, the theorem for comparison test, actually uses positive terms. So that's why I mentioned that. So imagine you have two positive numbers and this one is a finite number. Obviously, if this one is less than this, then this also has to be a finite number, which means that this series converges. So that is one example how we would use a comparison test. If I wanted to determine if this series converges, I just find a series where the terms are bigger that also converges. And if I know that this one converges, then obviously this one has to converge. Now the other way to do it is to, if you want to try, let's say this was a series I was given and I want to try to prove is divergent, it diverges. Then I just need to find a series where the terms are smaller, but where this series diverges. Because if the smaller one diverges, the bigger one must also diverge. Right, so that's basically what this theorem says. If an and bn, if you have two series, some are an, some are bn, where the series are of positive terms, meaning an and bn are all positive, and if for all the positive integers n, an is less than or equal to bn, then we have two things to consider. If the sum of the bigger one converges, then the sum of the smaller one also converges. On the other hand, if the sum of the smaller one diverges, then the sum of the bigger one diverges. Right, so let's look at some examples for this. Now, one thing to note, if you're given a question where you have to use a comparison test, you would, or you will most likely not be told what series to compare it with. So that you're going to have to figure out on your own. Right? But with enough practice and with enough experience, you will be able to come up with a series in a relatively short time to figure out what you need to do for any question you're given. So this question says use a comparison test to determine if the following series converges. Okay, so we need to figure out if this thing converges. Now, I'm just going to tell you now, if I see something with like this, where I have an n squared in the denominator, my first instinct is going to be to try to compare this with a p series 1 over n squared in some way. Now, I can't just automatically do it. I have to check to see it actually works first, right? Remember, the terms of this sequence has to be either less than or greater than terms of the next sequence you're comparing with, but we need to, whether it's less than or whether it's greater than, depends on whether we're trying to prove this converges or diverges. If we're trying to prove that this thing converges, we need to find a bigger sequence that converges. So we have to make this less than or equal to something. If we're trying to prove that this is divergent, we have to find a sequence that is a series that is less than it that also diverges. So we have to get terms that are less than this, but that where the series diverges. All right, now, like I said, I would look to compare this with 1 over n squared. So, well, before I even try to do that, I should determine if I could do it or not. Now, remember 1 over n squared, the sum of that is convergent, right? That sum is convergent. So if I'm going to use this with a convergent series, I'm trying to prove this is convergent, so I'll need these terms to be less than sum of 1 over n squared. Alright, so in this case, if you take n squared plus 1, that's obviously bigger than n squared, right? Because here we added 1, here we added, well, we didn't add anything. So this left-hand side is bigger than the right-hand side. Now when I take the reciprocal, the sign changes. And this is really good for me because what this tells me is that for every positive integer n, the terms of my series here are all less than the terms of the series of 1 over n squared. Right, now we know the sum 1 over n squared is a p series with p greater than 1, p is 2 in this case, so it converges. And therefore, by the comparison test, because this bigger series, remember this is bigger than this, because this bigger series converges, then this series which is given also converges. Alright, so you're going to need to practice this a little bit to get the hang of how to do this. Alright, now what about this question here? So if I see something like 1 over, like, ignore the minus 1, right, ignore the 2, this is, my instinct would be try to compare this with something with 1 over n, or even 1 over 2n if you want. Alright, now 1 over 2n is a divergent series, sorry. So what that means is I'm trying to prove that this thing is divergent. So I need to show that the terms of this are bigger than the terms of 1 over 2n, basically. Right? I need to actually establish that. Now, this 1 over 2n, right? 1 over 2n minus 1. If this 1 wasn't there, the number would be bigger because I'm subtracting, right? So subtracting 1 from 2n makes it less than if I had just had 2n. So here we have a bigger number. So 2n minus 1 is less than 2n. When I take the reciprocal, the sign changes. So 1 over 2n minus 1 is bigger than 1 over 2n. Now if I take the sum of 1 over 2n, I could factor out a half from that. And this here is the harmonic series, which is divergent. So the terms of this series are bigger than the terms of this divergent series. And therefore, by the comparison test, this series diverges. Right? You don't need to mention this. I just mentioned this here for you all just to explain why we actually have a divergent series. Alright, here we have a nice question. So use the comparison test to determine if the following series converges. So we have the sum 2 plus sine of n cubed over n cubed. Alright, now before I even try to figure out what's happening here, I would use, whenever you see sine of something like this in a series like this, use the fact that minus 1 is less than or equal to this, regardless of whether this, what this value is. Alright, this sine of n cubed lies between minus 1 and 1. So if I add 2 to the entire inequality, 2 minus 1 is 1, 2 plus 1 is 3. So the numerator here lies between 1 and 3. Right? Now, if I multiply both sides, or if I wanted, I could take this entire thing and multiply, or if I want, divide by n cubed. Divide everything by n cubed because n is positive. Alright, now if I divide everything by n cubed, I'll get the term of the sequence inside here. Alright, so I'll have 1 over n cubed is less than an, which is less than 3 over n cubed. And then at that point, you could try to figure out which one of those inequalities you want to use, depending on whether you're trying to make sure it's convergent or not. Now you're comparing, regardless of whether you use 1 over n cubed or you use 3 over n cubed, you're still comparing with the series 1 over n cubed because you could factor out the 3. Now the sum of 1 over n cubed is convergent because it's a p series with p greater than 1. You always have to say why it's convergent, right? So you have to say it's a p series with p greater than 1. And since this is convergent, what I want to do is show that these terms are less than something with that 1 over n, which is why I ignored this first part of the inequality and only consider the second part here. Right? Because I want this term to be less than or equal to something with n cubed in the denominator. Alright, once we get this, then we know sum of 3 over n cubed, we could factor out the 3. This is a convergent p series. So therefore, the original series I was given is also convergent. Alright, so that's it for the comparison test. Like I said, again, to emphasize this, you will need a lot of practice to figure out how to find the series that you're going to compare with. Alright, but typically what you do is you take your an and try to get some inequalities from it with a p series on either side somehow. And that will usually, then you could, depending on the p series they have, if it's a convergent p series, then you know you're trying to prove it converges. If it's a divergent p series, you're trying to prove it diverges. And then you can choose the appropriate inequality that you need for that. Alright, now the limit comparison test is a lot more straightforward to do. Right? It's a lot more to remember in terms of the conditions and stuff, but in terms of actually doing the test, it's easier because you don't have to worry about trying to make inequalities and things like that. Now, I'm just going to go straight into it. So the limit comparison test, also called the quotient test, you need to know both names, says if an, the sum of an and the sum of bn are two series of positive terms, we have three possible things here. So in all these three things, what we are going to do is work out, no, these are positive terms, right? We're going to work out the limit of an over bn. It doesn't matter which one is an and which one is bn, right? So the limit of an over bn as n goes to infinity. So if that limit is a finite number that is non-zero, so some positive finite number, so it's greater than 0, but it's finite, it's less than infinity. As long as this limit is a positive finite number, then both series either converge or they diverge. So if you knew, suppose this was the series I was given, if you take another series, sum of bn, and if you use this test and you get a positive finite number, then if this series is convergent, then your series is also convergent. If this was divergent, then your series is also divergent. Right, so this one is the one that you'll most of the time you'll use, but there are two other cases here that you should also bear in mind. If the limit works out to be 0 and the sum of the one in the denominator converges, so if bn is in the denominator, the sum of bn converges, then the sum of an also converges. Right, basically the bn is in the denominator, right? So if that converges, it means it doesn't go to infinity, which forces this thing to actually converge as well. Because if this went to infinity, you would have infinity over a finite number would be infinity, not 0. Right? Which is one way you could think of it if you want to. But basically, sum of bn converges, then the sum of an also converges, assuming the limit was 0. If the limit is plus infinity and the sum of bn diverges, then the sum of an also has to diverge. Right, notice they both do the same thing regardless of which condition it is. They do the same thing, but these two cases you have to be careful with the limit values. Alright, so let's use, what we're actually going to do is we're going to look at some of the examples we used previously. This here is the first example we looked at with comparison test, where we had compared it with 1 over n squared. Right, now when you're doing the limit comparison test with something like this, the most straightforward thing is to look for the highest power of n in the numerator, highest power of n in the denominator, and then work out that fraction and simplify it. And that series is what you're going to compare it with. So suppose this was like a n cube up here and you had like a n to the power 5 down here. Or let me use something different. Suppose it was n cubed up here and then one of these terms had a n to the power 7. Then n cubed over n to the power 7 is basically 1 over n to the power 4. So you're going to use 1 over n to the power 4 to compare your p-series with, to compare your series with. Alright, so it's much more straightforward to do than comparison test. So here we have 1, here we have the highest power of n is n squared, so 1 over n squared, we compare with that. Now we know the sum of 1 over n squared is a convergent p-series, because p is greater than 1. And what we're going to do is we're going to use this as an, we're going to use this as bn. Right? In this case, it doesn't matter which one you use as an and bn. It'll work out regardless. So we have the limit as n goes to infinity of an over bn. We need to simplify that. And now one thing I want to mention here is you'll notice I wrote it in this form, but you also have to remember when you're working out a limit where n is over positive integers, you're really and truly supposed to convert it to the domain to real numbers first. So the shortest way to do this, I find, is to write it like this. Simplify it first of all. Simplify it as much as you could. And then say, well, okay, if I take this limit and instead of n being positive integers, I had x being positive real numbers. If I take this and replace n with x, and x is a positive real number, then this limit I know is going to be 1. And therefore this limit must also be 1. So this is true since this limit is 1. Alright, this saves a lot of time in terms of having to introduce your function and so on. So you could do that here for the series questions, but for the sequence questions you should still introduce your function because we are mainly examining that up there. All right, so now this limit, the limit of an over bn works out to be 1, and then therefore from the quotient test, that is in the first of these, right? The limit is 1, that is between 0 and infinity. So therefore both series must converge or both series must diverge. The sum of 1 over n squared converges. That's the series we are using. And since this one converges, this one must also converge. Alright, second example. This is again another example we looked at above with the comparison test. So again, we identify the power of n here. Well, just 1. Identify the highest power of n here. It's just n. So we take 1 over n, and that is what we're going to use. So consider the sum of 1 over n. This is a p series with p equal to 1, so it diverges. Remember, it only converges for p greater than 1. Alright, so what we're going to do is use this as an, use this as bn, simplify it as much as we could, and now if I were to take this and replace n with x, where x is positive real numbers, using the properties that we did before, this goes to the limit of 1 over x goes to 0, so we just end up with a half, which means that my limit is a half up here. Again, this is between 0 and infinity. Now this series diverges, which means that the series given must also diverge using the quotient test. Alright, now we have another example here, which is different from before. Now you could have done this using comparison test, but it would be a little bit of work to actually get the thing you're comparing with. Now with the quotient test, it's much easier. So like I said, what you do here is you take the highest power of n in the numerator. In this case, the highest power is n cubed. You take the highest power of n in the denominator. In this case, is n to the power 5, and you divide those. That'll give you 1 over n squared, and therefore that is what we're going to use as bn, the sum of 1 over n squared. Now n, this here is a p series with p greater than 1, so it is convergent. So we record the limit as n goes to infinity of an over bn, simplify it as much as possible, and then we switch to positive real numbers and say, well, the limit as x goes to infinity of this same expression with x instead of n. This, well, we know 3 over x squared and 4 over x to the power 5 both go to 0, so we just get 7, which means that this limit up here must also be 7. Right? Again, this is a positive number between 0 and infinity, so therefore, since this series converges, this series must also converge. Alright, so the last test here that we have is the ratio test. So we'll first look at what the test is, and as before, we'll look at some examples. This time we have a series sum of an. This time we're not actually going to use any second series to compare it with in any way. We're just using the series itself. What we're going to do is work out the limit as n goes to infinity of the absolute value of an plus 1 over an. And we're going to let that be L. Now L could be a finite number or it could be infinity. Doesn't matter. Alright. Important things here, two things. One, this series does not have to be positive integers. For both of the series above, right, for comparison and for limit comparison test, both of them had to be positive terms. They couldn't have any negative terms. But for the ratio test, it doesn't matter. You can have terms that are negative. Second thing though is because of the fact that you could have terms that are negative, you need to have an absolute value here around this to make sure that whatever you get is always going to be positive. Right, so it's the limit as n goes to infinity of the absolute value of an plus 1 over an, and we're going to let that be L. Now an plus 1 over an just means that, well, I take this, I replace n with n plus 1, work that out, and then plug in an there and figure out this limit. Alright, now if this limit L is less than 1, for example, let's say it's a half, it's 0, it's a quarter, something like that, then the series converges automatically. If it's bigger than 1, then it diverges. It doesn't matter whether this is 2, 3, 4, or if it's infinity, it doesn't matter. It diverges. And if it's equal to 1, the test fails. So you have to be careful here. If you ever get this limit being 1, then you have to use a different test to figure out what it is, which means you'll have to go to the comparison or the limit comparison test. Alright, so we have an example here. Use a ratio test to determine if the following series converges. Alright, this is a little different from before. So you'll notice that the ratio test questions tend to be different from the comparison and the limit comparison test questions. Whenever you see a question where an is a ratio of two polynomials in n, meaning something like this, something like this, or even something complicated like this, as long as it's a ratio of two polynomials, then either the limit comparison test or the comparison test is what you want to use. Alright. But also, as I was saying, that always remember the very first thing you should do is not even any of these tests. The first thing you should do, unless you're told to use one of these tests, then yes, go ahead. But if you're not told which test to use, the first thing you should check is the divergence test. Right now, I believe all of these series here would pass the divergence test. This one does, right? Because the limit of an will be 0. Alright, this one is not so easy to work out. But the point I was coming to is whenever you see something that isn't like a ratio of polynomials, whenever you see something with n in the power, or if you see something with a factorial, then automatically the only thing you should be using is ratio test. Right? You should go straight to the ratio test. Again, assuming it does satisfy the condition that the limit is 0, if you could have worked it out. If you can't work it out, or if you see anything like this, then try the ratio test. So, ratio test says we have to work out this limit. N goes to infinity, absolute value of an plus 1 over an. So we have to work that out first. So I let an be n over 2 to the power n. Now it's always nice to define an as this because that will help you work out an plus 1. So an plus 1 is just going to be, well, n plus 1 over 2 to the power n plus 1. This here is an plus 1. And then we put an in the denominator. Now you have to simplify this and you have to be careful when you're doing it. Right, now everything inside here is positive, so I could drop the absolute value. That's why it goes away. So to simplify this, I could take the reciprocal of this and just multiply it instead of dividing. Right, so we get this. All of this is inside the limit. Alright, now the 2 to the power n plus 1, whenever you have something with n in the power, you're going to have to use this trick. So 2 to the power n plus 1, I could take this as 2 to the power n times 2 to the power 1. Alright, so 2 times 2 to the power n. The reason why I would do that is because this will cancel here. And you end up with n plus 1 over 2n. What you're going to do is again simplify it as much as possible. Alright, so we divide throughout by n. And then you're going to take this limit and replace it with a limit where instead of n we have x being positive real numbers. Work that out, right? That answer is a half. Therefore, this limit is also a half. Right? And now you have to be careful with the ratio test, right? Remember, we want the value to be less than 1 for it to be convergent. A half is less than 1, which tells me that this series is convergent. Right? Also, make sure you specify which test you're going to use if it isn't given. Alright, next example. So here we have two things. We have n in the power and we have a factorial. Remember, when you see either one of those, you typically need to use ratio test. So again, we let an be n factorial over 3 to the power n. We work out the limit absolute value an plus 1 over an. Right? Again, everything inside here works out to be positive, so I could drop the absolute value. And then I flip this and multiply it instead of dividing. Now, two things here. The 3 to the power n plus 1, I could write as 3 times 3 to the power n. And the 3 to the power n cancels, which is why I end up with a 3 here. The second thing is, the factorials. Remember, n plus 1 factorial is n plus 1 times n minus 1, etc. This is really n plus 1 times n factorial. And the n factorial cancels, and you're left with n plus 1. Right, again, you need to replace your limit with x as a variable, where x being positive real numbers. This limit here is infinity, right? So it means that the original limit here is also infinity. And when that happens, as long as the value is bigger than 1, then by the ratio test, the series diverges. All right, last example here. All right. So this is a little more complicated now, and this is more like a kind of question you might see that you're asked to do. So here we have n in the power in two places. As long as I see it in the power at least once, I know I'm going to use ratio test. Alright, so what we're going to do, again, let an be this entire thing, and we're going to work out the limit as n goes to infinity of the absolute value of an plus 1 over an. Now, it just so happened that in these three examples, everything was positive, so I could just drop the absolute value right away. But you just need to be careful, because sometimes there might be a negative inside here, and you can't just get rid of the absolute value. You have to make sure the negative sign goes away first. Alright, now be careful when you're working this out. For n plus 1, you'll get 3 to the power 2 times, in brackets, n plus 1 minus 1, over 7 to the power n plus 1 times 2 n plus 1 plus 1. Right? This simplifies to 3 to the power 2n plus 1. And then this is just 2n plus 3. Right? Flip this, multiply it. Alright, so with this now, to simplify this, the 7 to the power n is easy, because you could just write this one as 7 to the power n times 7. And the 7 to the power n cancels, we're left with 7. The 2n plus 1, the 2n plus 3 remain. This 3, the power of 3, you have to be careful with. So you could think of this as 3 to the power 2n times 3 to the power 1. You could think of this one as 3 to the power 2n times 3 to the power minus 1. The 3 to the power 2n cancels, and you get 3 to the power 1 divided by 3 to the power minus 1, which is the same as 3 to the power 1 plus 1, so 3 squared. Alright, the 9 over 7 that you get there, you can factor out to the limit. And then this we need to work out, so we divide throughout by n, simplify it. And then I switch, again, I am actually doing it this way and then coming back and explaining why I did it that way, right? So the reason why I can do this, why I can go from this step to this step, is because of this. Because if I replace this limit with, if I replace the variable with x being positive real numbers, the limit works out to be 1. So therefore this limit must also be 1. Alright, the value I get is 9 over 7, which is bigger than 1. And therefore by the ratio test, the series diverges. Alright, it is very important that you get a lot of practice, as much practice as possible, solving problems using these three tests in particular: comparison limit, comparison ratio test. There are 2 links here that give additional problems on these, so please try them, practice them as much as you can, and then you should be good to go. Alright, so we're finally done with this. I will end this here.